Now we continue with the Energy Bus connector family. There we can see 4 connector systems, and each of these connector may have sub-connector types. So we have 2 levels here. One level is the 2 members of the IEC TS 62196-4 standard series. This is the one, the Energy Bus M. It's the standard sheet 4 Roman 1B, and the Energy Bus NFC connector is the standard sheet 4 Roman 2C. So both of them, they have the same basic functions. They communicate and transfer energy, but they are for different applications and use cases. I described earlier, this one is for the vehicle to the infrastructure. And we learned before that the cable is always with the device and the socket is always with the infrastructure. And over here, the socket is technically on the device, which is like the battery. But there are also applications where the socket is on the vehicle. And you have a cable coming with the charger. Over here, these are the new kids on the block in the Energy Bus connector family. And there we have 2 connector types, which are for batteries, which you can remove from the vehicle. And yeah, they are grouped here because they are both from the Energy Bus member Unicorn and they are both from the Energy Bus member Rosenberger. These have a lot of technical similarity each. And yeah, Johannes was the person behind this connector family.
Yes.
And this is already elaborated and evolved over now more than a decade. And there's many stories about it, a lot of experience gained.
Yes.
And this is something which is still rather new.
Yeah.
Maybe you can tell something about the basic principle of it and about the specifics of these connectors.
Yes. Yes, we come from the history from the Rosenberger connector long time ago. I think 50 years or how long?
Well, this was 2008. We started the working groups with the Energy Bus members.
70 years. Wow.
17 years. Yeah.
Wow. The important is you have plus and minus always for transferred energy, and in this old style we define together as a group of energy bus. We say we need some power plus minus 12 volt and we need some communication. There we find out that the CAN communication is the best what we can do in the moment. This I've learned, sometimes it works wonderful, sometimes small connector makes a little bit trouble. Then I have the idea because 10 years ago, near-field communication was totally new. And for me, it was very impressive that it is possible with the near-field communication transfer information and transfer also a little bit power, like the 12 volt what we have defined here. And the nice thing, we need no contacts because it's wireless and it's near together wireless. That's why near field named inside. So I'm thinking, wow, that's the perfect solution for bring this in a connector. Always have the 2 pins for the power because these 2 pins also with the plug and unplug cleaning and also with the high current it cleans the connectors. And the small pins makes always a little bit trouble, so you must use a lot of gold material to solve this problem. But with salt water, for example, they have also problem of corrosion and things like this. Yeah, together with my car and the experience how public charging are working. I have also the experience that the communication makes a lot of trouble because of the connector and of one stable communication protocol. And there we was happy as a group that CANopen Automation helps us with the communication because they do it since 25, 30 years.
1992.
1992, wow. So 33 years now that Bosch described the CAN, and at the end CANopen as a group described how industrial machines working together over CAN bus. And that's important because there is a lot of knowledge in. There are now over 30 years knowledge about a lot of engineers. And that was very helpful for us. That we also learn in the other group with the cars that they have now about 5, 7 different communication protocols between the car and the charging station. And we have here only one protocol, and that makes it much, much, much easier. Yeah. On later I describe a little bit on the physical material, how it works. You see there are 2 pins, you see there are 3 pins. That was the idea because the car manufacturer says our group should be under the group of public charging interfaces for cars. So the limit they begin with the voltage on DC is 120 volt. But we say clearly 120 volt is too much for touchable voltage in small vehicles. So we find first together in the standardization that we should reduce the voltage as a maximum to 60 volt. So this small connector for small vehicles is limited to 60 volt. And the extra pin we see later is for the high voltage. The same technical things we have integrated. Oh, I forgot the lock, also very important. Like you know from electric cars today, you can the plug, if you plug in infrastructure or in your car, is also locked today, that no one can stolen your cabling. This is some functionality we forgot here in the beginning. Only in a special infrastructure project together with Abus, we have the locking version, but then the connector increases with a heavy cable, for example. So the locking functionality can lock this connector. We see also on the samples later. And the second one we built for batteries have exactly the same parts inside. Means we have plus minus. We have some locking functionality. This is totally new for batteries, that the connector also do at the same time the locking. So these pins can going in and out of the case and make this locking possible with some small motor. So if the battery is stored in a frame, for example, when the pins are outside, you cannot push it out of the vehicle. If the pins are going back because switch off, then you can take also the battery out of this. New invitation with bringing this to standard. This means always it is allowed that everyone can produce the charging infrastructure and the battery connector. That's important for me, that we are be interoperable for the future of these devices. Let's see how it looks on this table. We have the 60 volt version with plus and minus, and here on the top is integrated the near-field communication. So it's possible with this near-field communication integrated in this area also some electronic as a gateway, because In the cabling, it is possible then to have the CAN bus and communicate with the vehicle and also with the battery at the end of the day. The same is also the connector for the infrastructure where you can put it in. There is a motor and motor control who open and lock this connector. And it's also possible to have on this position electronics as gateway to bring from near-field communication to CANopen protocol to the energy bus protocol, and then working together with the charger to deliver exactly what the battery and the vehicle want to have. We have here a second version, and you see, oh, there is now this third pin, and this is our high volt pin. So we have here the 0 volt and the 60 volt, and here we have the 0 volt and minus 120 volt in the definition. Why minus 60 plus minus 120 is at the end 180. This means this connector is able with 60 amps, 60 volt to have 3.6 kilowatt at maximum. This connector can have at 120 the 7.2 kilowatt, and with 180 volt about 11 kilowatt delivery. And this is enough for the small vehicle, and this is also enough for very fast charging for electric bikes in the future, if the battery is able to handle this. So please not use this in your bike today with 60 amps. This will destroy the battery immediately.
That's why we have communication up front. And maybe an interesting story how this happened. This is really joint work between many parties. And for example, I remember very well, we had a meeting at Kusterding, which is the headquarters of Bosch eBike systems, many years ago, and there Bosch requested that we have, for safety reasons, the 60 volt pins separated from the 120 volt pins physically. So that's why we came up with the third pin, and actually also the subject with the locking was mainly pushed in by BMW motorcycle, because BMW motorcycle, they did a lot of testing with the arcing when you unplug a DC plug while charging, and there we found severe damage on the contact points and the contact material due to the arcing.
Yeah,
and that's why they really requested to have the locking mechanism. So there's a lot of knowledge from different companies and stakeholders went into this final design.
Yeah. And also very important, there was the discussion about security. I was in the history always very open. CANopen says open. And also there the company says, oh, our CAN bus, please not open. We want to have our information in the vehicle, but not give it to the public. And this is now clearly done with the gateway, what is integrated, and using near-field communication. So the CAN bus, what coming up to the connector, it's clearly the manufacturer can define exactly what's transport on the near-field communication and what is part of the vehicle. Most time it's only needed the information what is printed on the label of a connector for today. So exactly we have there digital the information, what voltage, what current should be used, and what is the maximum and at the end the information which company built this and which serial number has this connector, that it is very open information on the open end, And with near-field communication, it's very easy to make identification and authentication. That's the daily work of credit card. And so we have a lot of nice feature building in the field of credit cards. We can use it also at the end for identification, nearly payment, for example, and things like this. And that's a wonderful situation for a secure system at the end of the day. That's more difficult with open conducted canvas in a moment.
So it's electrical separation is delivered between the infrastructure and the vehicle side. And anyhow, I think looking back, these 15 years, this was an extreme difficult way to get there. But also now with the projects which we have been able to do, thanks to the European Union project, and now thanks to the first mass production samples, this has evolved very well.